What I was saying is the following. We saw, for instance, the Q is configuration space. And there is associated with Q bar universal covering space. And the main characteristic of this one is it is simply connected. So universal covering space is by definition simply connected. Then there is a group which is I1 or Q. This is the fundamental group of Q. I'll give you examples. Okay. This acts on Q bar reading. Reading is just to fix any element here has to no fixed point, right? So as said, this Q bar coordinated by Y1 of Q is Q. Right? So you identify points which are connected by Y1 of Q. So you get this bundle. If you want here this bundle I1 of Q acts on Q bar, getting projection map by. This is structure group. Okay. This is a bundle, you know. So this is a group which acts on this bundle space, given the quotient space. Okay. And we want to do quantum theory on this. So what I wanted to do today was examples. Let me first start with a very easy example. The easy example is, just look at playing with n holes. Okay. So it's a plane at x1 up to x7. Okay. And these holes are positioned here, whereas the no two holes coincide. This zero does not represent a hole. Zero does not represent a hole. X0 is not a hole. It's a point in the complement. These are the holes. These are the holes. So this is a huge group. So it is given by Dirichlet's relations. Okay. So what is it? Dirichlet's? Let's see. A particular derivative which I called x1 0, x0 to x0, okay, looping okay, this point x1, okay, in, if I go like this, is anti-clockwise direction. Okay. Like this. So I take a curve like this. Okay. Okay. It does not enclose other points. Without enclosing, choose a curve gamma 1. Okay. Without enclosing xj, j larger than 1. So there is none of the other points are inside it. So it is a loop like this. Okay, go like this and coming back. Okay. Now, so one loop is L1 is a homotopy class of gamma 1. Okay. So you take all loops like this in going, so you can distort this or whatever it is without crossing the other points, okay, and identify them, you get one element. Okay. Similarly, Lj. Okay. Then pi 1 of Q is a free group. You know what I mean by it. Okay. Generated by Li. Free means any, okay, free means, okay, that free means only relation is, okay, L1 inverse is identity. Li no, I don't have brackets. There are any brackets here, no? Li inverse is Li inverse Li is identity. Namely, the only relation is to go around like this, go around like this, they give you one identity. There is absolutely no other relation. Okay. So any word you write in this is a different element of the group. Is very huge. Okay. This group played with n holes. Clearly, if you try doing Aharana boom relevant for Aharonov boom. Aharonov boom. Effect. You can imagine Aharonov boom normally is done with one hole, okay, and you consider paths going around it, okay, and so it is really the phase is coming because of the phase you pick up as you go around, and if you have a non-abelian flux, you will get a non-abelian Aharonov boom. Okay. So this one, you can imagine that there are, for example, non-abelian fluxes through these holes. Okay. So you can say that these are Wilson loops, okay, with a flat connection. Then there is a flux in the Wilson this path ordered integral, and that gives you a representation. Okay. But any flux you can put, they are huge, is really incredibly huge. Okay. Okay.
But then this relation is true for all groups, right? Any group will have an identity element and their operation. I mean, the way you define an inverse operation that depends on. So it will have this relation. Any group will have this relation.
Which relation?
I mean, this inverse.
That is always true, because you are just going backwards by the same route. No? So you can undo the loop. Okay. But there is an obvious relation, and free means there is nothing else. Yeah? Not the free means between L1 and L2 there is no relation. For example,
Yeah, that's what I'm talking. There can be only
one such group, free groups. No. There are many free groups. Okay. And free groups.
When you differentiate between other different groups.
A free group is simply, if you give me n generators, any n generators, any n elements, alpha, A, B, C, D, you can generate a free group from it. You say that all lectures in A, B, C, D are different, and say that A inverse.
If I put some different groups, that will amounts to imposing different relations between the generators.
From the free group.
No, I mean Generally, we identify these groups by relations between their generators.
Yes. For a continuous group, normally you don't do that because the relations are more complicated. So,
you are saying that there is no other, absolutely no other relation.
For this one, there is none. This is a discrete group. This is a discrete group. Okay.
Can you give 2 examples?
This is the example.
No, 2 different free groups.
Take n. This problem is for yes. Take n letters. Any n letters. There is a free group. The free group is characterized by only the number of generators. Free group on n generators, if you say, it is completely fixed. If you say, if you change n, you will get another free group.
That's what I am talking about. I mean, for particular n, there can be only one such group.
There is only one such group.
That's what I am.
Okay. Okay.
So this orbifold groups are example of
Orbifold.
and this abelian G square, say for example Z3 rotation.
But they are orbifold. They are normally discrete, finite groups.
Yeah.
They are not free.
They are not free.
For example, cyclic groups are not free.
Cyclic groups, so they are not free.
They are not free because some power is 1.
Yeah.
Here there is no such thing.
So but we needed only one relation, so they are also like
That is, this is not even a relation. Anything will have an inverse. This is simply the statement that every element has an inverse. Okay? That's it. Okay. Okay. So orbifold cyclic groups are not free.
because they have fixed points or something.
No, that is the action of the group on some space. I am not talking the abstract group. Okay. As a group, it has no, should be no relation. But when you look at a representation, there may be relations. Okay.
So here, for instance, if I want to look at the loop that covers, say, 2 of the nodes, so that will be
L1 times L2. But it is just concatenation. Okay. So the physical meaning is it is double the flux, or you add the flux, but it is these are non-abelian fluxes in general. So if you want a representation, you put some flat connection. You know what I mean by flat connection with curvature 0, G inverse GG. Okay. Around each of these points, then you write the Wilson lines. There it forms a representation. Okay. Depending on what flux you put, you will get a representation.
Another question. So, when I draw this thing, so L1 is the loop around X1. Similarly, I can draw a loop around X2.
X2, yeah, L2,
So,
L3.
so these loops can intersect between loops.
Intersection is no problem. No problem. It's only continue intersect. There is no statement that when you traverse a loop and make another loop, you cannot cross the other first one. But it should not cross a hole. Okay. Hole is not there. It is not there. Okay. So now I will tell you something which is very important for condensed matter and also conformal field theories, which is braid Sn and braid group. This is
Sn means
permutation group on n objects. So let me look at Sn. First, let me show you something. It is known that, but how it comes as a statistics group, I will show you. Okay. Sn has a presentation I will tell you what I mean by presentation. With normally they write sigma I plus 1, I going from 1 up to n minus n-1. Okay. Then the relation Si sigma I plus 1 sigma I is sigma I plus 1, sigma I plus 1, sigma I squared is the identity. Okay. This relation is a braiding relation. It comes constantly when you work with vertex operators in conformal field theories. Okay. This one here. Now I want to show you. This is the this is known that this is a this is a presentation of SN. Okay. Presentation means you write all letters in this. Think of this as transpositions of adjacent objects. I will show you how this comes about. Okay. So you write all letters here, but you can simplify them only by using this relation, and that's it. The inverse is sigma I plus 1. These are the only relations you should use. Okay. Then you can prove, it's a proof that what you get is the permutation group. Now what do I do? How do I get it? So consider Rn. Okay.
So here you are actually drawing a loop around sigma I plus 1.
I will show you what it is in terms of manifolds and covering spaces. Okay. This is simply a group. Okay. This is some group. We don't know what it is. Okay. It happens to be a permutation group. You need a proof, and there is a proof. By the way, there is some notice or something there. No. What happened?
The camera is
Okay. Who is handling the class there? So you have put a notice there or something.
Actually, no. I don't.
So how do people know?
Last one is that he will wait there and somebody.
Okay. So consider Rn. Let me consider n larger than or equal to 3. Now I will consider on Rn. Let's say not call it Rn, Rm. Okay. Take n distinct points x1 up to xn, okay, from Rm. Okay. They are different. Okay. So xi is not equal to xj. Okay. Then this thing, okay, xi x1 up to xn, okay, is an unordered set, is unordered set, okay, invariant under permutations of xi. Okay. There is a notation. Claim is it represents the coordinate of n identical particles. The fact that it is identity is in the statement that I cannot say particle 1 is at the position 2 x2 and particle 2 is at position x1. Okay. So, it is unordered, it is a n points from Rm of cardinality n. Okay. Okay. Then okay, the configurations, their configurations, the configuration space is Qn, okay, which is the set of all x1 up to xn. Okay. So, it consists of xi in Rm xi is not equal to xj, I is not equal to j. I will tell you the meaning of not allowing them to, really what I will tell you, if meaning of not allowing them to overlap, there is some meaning, you get conical singularities there. Okay. In this space, if you allow them, you get conical singularities. Okay. So, you need special treatment, I will come to that later. There are open problems there, really big open problems there, but I will come to that. No? Now, I want to compute the fundamental space of Qn. Okay. So, for that is in 3 dimensions. I am thinking of this whole thing as 3 dimensions. So, what we are doing in 3 dimensions is, okay, so we choose, okay, some fiducial points, choose, call it x0, and this is this unordered set. Okay. So, I choose in 3 dimensions, 3 or higher, is 3 or higher. So, I am choosing x1 0, xn 0, and here I have the same point I write xn 0. Okay. Now, I will write a loop here, is, let me call it is sigma 1 2. Let me write sigma 1 2 here. What is a loop? I move, think of it as is a loop. So, this is in 3, this is my Rm, these are living in Rm, this is living in Rm, and this is, if you like, time or the homotopy parameter, curve parameter. So, T, the parameter of the loop, is going this way. What do? I go and move this to this point, and this one, let us say, move it behind. The rest I do not move. This is sigma 1, the loop, the homotopy class of this loop is homotopy class, class of loop in figure. Yes? This is the braiding, but in higher dimensions, it won't give you the braid group. I will show you why. 3 and higher, it won't get be the braid group.
Why do you need n greater than equals to always?
N equal to 2, something special happens. Okay. N equal to 2 is special. N less than 2, wild things happen. Okay. And we have, in fact, there are other, I will show you. Something we did and it came back in, I found that it is come up in graph theory, what we did long ago. And it has some applications in network, what is it called? Mesoscopic networks. Okay? But
it's like you are evolving these n points with respect to some variable e. Can you get that?
you can imagine it as taking the 2 points, and this is my initial point, and I am gradually moving like this.
Okay, again, is this like, when you are just describing this permutation in terms of this diagram, right? Is it just a permutation of this?
This is a permutation of 1 and 2. It's a permutation of 1 and 2. Is a permutation, think of as thought of as adiabatically achieved.
So now I just want to what suppose again I'm just going back to the logic one thing over there. So there, for example, I do this circle, okay, and I identify opposite points.
That is unfortunately singular, I know.
Yeah. So can I write that also in terms of this kind of time? How do you represent those fixed points?
There is no fixed point this is actually a curve. Okay? In the configuration space in particular, this is a closed curve. Okay? Closed because I am coming back to the same. So
Just one thing, for what he is saying as orbifold, I mean, for n equals 2, Sn and S2 can more or less mention as Z2, right?
S2 acts on a circle,
Yeah.
but it acts, that is, the identification is, see, what you are doing, those people do, you people do. Is S2, you identify this point with this point, this with this. But that is singular, right? Because, I mean, you have to tell how you are identifying, no?
Yeah, this thing.
So,
You are identifying this with this. You are identifying this with this. So what happens here? You get a singularity. Okay? It is orbifold. Okay? That's not the kind of thing I am considering here.
So that's why you are saying that n greater than, I mean, that's why you have this n.
No. I will not consider orbifolds. I will consider smooth things. Okay? And the orbifold picture will come. I'll tell you where it comes. If you allow these coincident points, then you will start getting conical singularities. Okay?
So you remove the coincidence.
It has to be removed, and I'll tell you how it has to be handled and why it is practically impossible. It's a completely open problem to do what to do here.
Why are you getting the singularity?
Huh?
How are you getting the singularity then? Means what do you mean by singularity in that context?
When
On this
Of this loop, say.
not on the loop. If you take n points in the permutation group, see I am identifying what is this? What is a universal cover? It is simply the ordered set. The universal cover will be the ordered set x1 up to xn. Okay? Ordered means this space of non-identical particles will be, but if they are coinciding, the permutation there will be fixed points. Okay? For example, if 1 and 2 coincide, the permutation of 1 and 2 doesn't change it. So there is a fixed point. When you have fixed point, you get this conical singularities in the quotient. Okay? Right? Because if you take a line, and you know the example, right? If you reflect, okay, but just a middle, so middle point will become singular. Okay? Right? So that's why you are removing it. But quantum mechanically, you cannot remove it because the Hilbert space doesn't care about points. Okay? So you get problems with boundary conditions. Okay? And I'll tell you, there is a completely open situation there.
So when you say that there is absolutely no other relation for a free group, but when you call it a group, there is of course a closure relation. Right?
Closure? What do you mean?
I mean, the way we define we write an algebra.
No, it may be infinite. This group, you are talking about a plane with n holes.
The group has to close under some operation.
Close, no. For example, the group with n holes, plane with n holes, that is an infinite group. There are infinitely many distinct points there. It is an infinite finite group, infinite countable group. The break group we will see is an infinite group, infinite finite group, infinite countable group. Of course, rotations form an infinite group because the number of elements is infinite, it's a manifold. No? But this is infinite in a different way. Okay? The cardinality of this set is those are integers of many, in fact, how many? No, it's not even infinite, I don't know what it is, because plane with n holes, not this. The each letter has cardinality infinite, no? Each letter. But there are infinitely many letters. So I don't know how, there must be something in number here.
That's also infinite.
That is generated by one element, yes.
Yeah, but there is an infinity element like this, and you have the relation that you multiply or add anything, any element to another element, you also get an infinity.
See,
So, but that kind of relation has to be.
so for example, L1, that loop I wrote, L1 generates a group Z, L2 generates a group Z, completely different. Okay, L1 L2, huh?
What do you get?
Set of integers.
Oh.
Then L1 L2 generates another Z. These don't commute even. Then L1 L2 L3 generates by itself another Z, and none of them commute. Okay. So if you try counting, I don't know, maths people would have studied this, but I don't know this. It is a group. The axiom is a group as I said. Group has some axiom.
What is the binary operation?
Huh?
What is the operation for that?
Multiplication. Multiplication.
Multiplication.
Hmm. Multiplication by concatenation.
Closes are not multiplication.
Huh?
That's what I'm saying.
Close means the set. You say A, B is there.
Result will always lie inside it.
By definition. By definition.
That's why we became relation.
Huh?
Why do you say that? So that relation coupled with this relation is only there. So that's the.
No, if you give me any set of letters, I can make it into a group by saying, in my group I will write all letters in ABCD are in the group, I will say, by fiat, it's a group. Okay. It is this group. It will become more subtle if you start talking about topology of this group, because it is infinite set, you may ask. Okay. Now,
So I don't understand the configuration space of this. Sorry, the configuration space. So it's x1 to xn. These are particular points or
any n points,
any n points.
Huh.
So what is this configuration space?
it's just n particles. Like suppose you are here, you can go anywhere in the, that's it. But you cannot collide, that's all, only thing.
So I'm just excluding points where x1.
Equal to x2, and they cannot sit on top of each other. So I want to look at sigma ij, sigma I plus 1 is defined in the same way. Okay. Now the relation, what is most interesting is this relation, sigma I plus 1, sigma I is equal to sigma I plus 1 I want to prove this. So here I have I plus 1, okay, yeah. Oh, by the way, sigma I plus 1 by definition is sigma I. Here I have put two indices there. So I read, because I am only looking at transpositions of adjacent letters, I can simplify it. So that's how they write it. So I plus 1, I plus 2 I take, and I draw side by side I plus 1, I plus 2. Okay. Then here also I plus 1, I plus 2. Here I plus 1, I plus 2. Okay. Now first let me do this. The sigma I transposes this. Should be careful. It goes like this. And goes like this. Next one is, so this goes, I should be careful, this goes underneath. Okay. Next step is sigma I plus 1. So this goes over, this goes underneath here. Okay. Then again sigma I, this goes over, this goes underneath, and this goes here, and this is my closed loop. I should have. Okay. Now let me look at this loop. Here, I don't do anything here, but I go. This goes over. This goes underneath. Then I extend these two, so this goes over, this goes underneath, then I come here, so this goes over, like so. If you stare at this, you can see that these two loops are the same up to homotopy. For example, this loop goes over both the others. Okay. This one, this also does the same. Right? This one goes underneath the one from I. Yeah, this one goes underneath the one from I, like here also, and goes over the other one, which is this here, and the last one goes underneath both. Okay. If you think of it as strings, by putting two things you can easily move. So this is clearly homotopy. Okay. Now one point to notice is this relation. Okay. One OK also for n equal to m equal to 2. This calculation I did, this can be planes. Okay. So this could be this. So you notice immediately that what I have got here, if I now join the upstairs with the downstairs, what will I get? I will get a knot. Right? So for n equal to 2, which is 2 dimensions, in m equal to 2, if we join top with bottom, right, we get a knot. If I just join this, okay, I get a knot. So you can see immediately that the break group has something to do with knot theory. In fact, since break group has strongly something to do with conformal field theories, you can see how these things get connected up. Okay. This relation is what was used by Jones, that if you close it, you get a knot, and this break group, some with extra relations, gives something called Hecke algebras, which he used, and Witten used it, same braiding, but he used conformal field theories. Okay. Sorry?
Where it occurs in conformal field theory?
Crossing
symmetry or something in the 2-point functions.
Break group turns up in conformal field theories as see, the break group is a statistics group in 2 dimensions. Okay. In conformal field theories are 2-dimensional theories. So when you start talking about braiding, so you have in what you normally have conformal field theories, you have a, say for some Riemann surface or something, you have holes, and each hole you have a hole representation of the Virasoro algebra. When you are trying to move these holes around, in moving the holes, what you are doing is to braid. So that is where the braid group comes. Okay. As a statistics groups of conformal field theories living in each of these holes. Okay. And when you move around, the braid group changes the representations and you get conformal blocks. Okay. So some complicated relation is there. Okay. Okay.
This moving around is somehow very, when I construct this 2-point and 3-point function in conformal theories, the form of the functions almost, they always come with some, if xi is say 1 by x1 minus x2, they'll all be like x1, 2, x1, 3, x3, so that
right.
they'll all invariant of
right.
this conformal symmetry. So
It's the same. This tells you your number of vertices of, if you do vertex, you can move them, move one from one to the other, first moving first 1 and 2, then 2 and 3, then 1 and 2, okay, or the other, this one. You get this, you should get the same answer. If you do that, you will get these braiding relations. So this leads to this R matrix, if you are heard about R matrix and so on, okay. Yang-Baxter relations, you get it. This relation is a variant of, this is where, from where the Yang-Baxter relation comes, okay. One way to interpret them, okay. Now,
so joining top and bottom is for each of these, or joining top with this bottom?
take this thing, not this one, take this one, identify this with this, this with this, this with this. Huh? You get a knot in 3 dimensions. This is only in 3 dimensions. No. What happens to sigma I squared, okay, for m larger than or equal to 3? This is where the difference comes. For m, what am I doing? Okay. This corresponds to I plus 1, right? Now I am going upstairs here. I am going upstairs here. This is what I am doing, right? Twice. Right? So what this is doing is, for example, I can straighten this loop without doing anything. So I can straighten this loop, okay. So I can, this is homotopic too, okay. I straighten this loop, but I put a hole here. This thing is going upstairs, and this one, what it is doing is going like this and going like this. So what I have done is, this is equivalent physically in 3 dimensions. I got this I plus 1 x of I plus 1 coordinate, x0 y plus 1, right? And this point has started at x0 I and gone right around, right? In 3 dimensions, but in 3 dimensions I can take it out of the plane and shrink it to a point. Okay. So take this loop, take this gamma, take gamma out of plane, okay, and let it shrink to a point. Okay. So what has happened is, so sigma I squared is identity in 3 or higher. For m larger than or equal to 3. right? Right? So therefore the pi 1 of Qn is Sn. Okay. The universal covering group, if you like Q bar, what is Q bar n? Covering space is simply space of n non-identical particles. So it will consist of non-identical, no? Let me call it x1 up to xn, okay. Xi not equal to xj, I not equal to j, okay, and is an ordered set. Ordered means if we permit, I get another point. So I know if particle 1 is at position x1, particle 2 is at position x2, and so on. So this is my universal covering space. This is simply connected. If I act with permutation and quotient it, permutation is this, I get back the space of n identical particles. Now there are some funny things. If I look at m equal to 2, it is not true as gamma encloses in the previous picture this point x0 I plus 1. It is inside. I have got a loop, but there is a hole in the middle, and there is nothing to lift the curve, right? So there is a hole in the middle. I am stuck. So if you drop this relation, we get, hence we get what is called a break group. This break group is given by this generated sigma I, okay. Sigma I plus 1 sigma I is equal to sigma I plus 1. This is the definition of break group. You just drop the statement that the square is 1. Okay. Square, so that's all. If you allow the square, yeah. If I allow, if you drop that, there is only one relation you are dropping, okay. But this group is, okay, Bn is every element except, okay, identity is of infinite order. Huh?
How does this Bn follow from this?
This is a definition of the break group. It is it's a statistics group of n identical particles in a plane. Yeah? And then one proves in books that this is huge group. Every element has infinite order except identity. For example, sigma I squared. Sigma I is permutation. So sigma I squared, you get a fractional statistics. Okay? If sigma I squared is not identity, that means it's not fermion or boson. Okay, we get fractional statistics. Because a square double permutation doesn't give you 1. Okay, this is what gives you fractional statistics. So today I will say one more thing, then we'll continue. Here is a peculiar problem. Okay. Say Qn remark. This thing Qn has a boundary. It is not a manifold without, it is, I will tell you. Okay. For example, let us consider example. Okay. Let us consider two particles. Okay. Let us consider m equal to 3. So in Qn, so what happens here? Okay. I am removing the diagonals, no? So what is the dimension of Q2 is 6. Two identical particles, right? Just 3 coordinates for each.
What is that?
Dimension of Q2. What is dQ2? It is a set of all XX. So dimension is 3. Right? So this is a very strange situation, unusual situation. Suppose I consider, so this is not a regular boundary. So normally if you have a boundary, so this is, so codimension of this thing dq2 is not equal to 1. Normally if I have a plane in the boundary, you lose one dimension.
Yeah.
Okay, this is very
That's why it is twice.
you can count. So what is the first result? Stokes theorem does not apply. You cannot do partial integrations.
So why is it like this?
Why? I don't know. Not every manifold has a regular, what they call, it's not a regular boundary. A regular boundary is one which is smooth, of course, and codimension 1. There you can apply Stokes theorem. Here you cannot apply Stokes theorem. You cannot do partial integrations. It's not a regular boundary, but it is there. Okay? So, if you consider Laplacian, boundary conditions, for Laplacian, two particle Laplacian, I am giving you an example. Okay? So it is delta of x1 squared plus delta of x2 squared, not known. You don't know boundary condition as there is this so-called, there is this von Neumann theory which will tell you how to, but that is there, okay? But it is not very practicable. It is not in a form to use all the time. Normally you consider manifolds with boundaries, your Dirichlet conditions, Neumann conditions or Robin conditions. Here what do you do? Because you cannot partially integrate. Okay? All those things depend on partial integration to prove things. You cannot partially integrate, you cannot apply Stokes theorem. What do you do? Not know. Von Neumann theory applies, but nobody has succeeded in applying von Neumann theory here. Okay? So this is, I would not propose this as a problem because it is too difficult. I have some preliminary notes from friends of mine who are mathematical physicists, and they themselves got stuck. Okay. So this is a very strange thing. Raphael has written a paper on this long ago. In the case of fractional statistics, what are the boundary conditions for fractional statistics at this orbifold point? These are orbifold points. When you do partially, what is a corner? The corner is when the two wave function has two arguments the same. Okay, those are where you need boundary conditions. What do you put? You don't know. Dirichlet, Neumann, you don't know, because the whole thing dimension is wrong. Okay, compared to what we know. Okay. Okay, let me just finish. Okay. 1D. So networks. So this is what I did with Hercules, ELISA, and strangely, this is an interesting problem in graph theory. One electron here and one electron here, and they want to know how to exchange them. There are many ways of doing it. For example, to exchange this with this, I can first move this here, and then bring there. Right? You understand what I mean? Can take this, move like this, and bring it here. Then this is out of the way, so I bring it to this position. Then I take this and put it back here. Or I can move completely, right? Or I can take this and go on this side, go like this. Okay. So there are many moves, and that will be the fundamental group of this configuration space. How do I do quantum mechanics with that? And at the corners there are junction conditions which are more handleable. Given that, find the spectrum of the two electrons on this network, which could be your Fuller ring. So you can experimentally measure it. Okay? How do I do it? Yeah? If you take any model where the what they call free electron model, there is, you have bonds and the electrons are going along the bonds, you get these things. Can you calculate it? Okay? So we did some work, but it became, we did not know how to control the situation at some point. So we published something, we stopped. But last 2 years ago, I got some work by some mathematician in graph theory, where they were able to make precise assumptions related to locality or something, and they were able to present the group. So that is something that is actually doable and might have applications in people doing mesoscopic networks. People like Janavar in Bhubaneswar, you know him, or people in Bangalore, okay? Or even here, people like Bhaskaran may be interested, but it is an important problem, okay? And it is not difficult, because the place we got stuck seems to have been resolved in a very nice way. When I read it, it looked like that. Okay? So there are many things, but also there are other things, like, I mean, we wrote a paper on statistics of closed loops. This will be related to your question of geons. Instead of doing point particles, suppose you do loops, what happens? We did this. This is very close to what happens in gravity. First is you can exchange them in 3 dimensions. Okay. Then there are other loops where I can take this. Suppose it is oriented or unoriented. I can flip it like this. Okay. Just flip it, each one. But there are more moves. I can take this, go through the middle and come back. Because there is nothing inside, so I take this, go to the middle and come back. Okay. Then it cannot be, right? These are all moves of the configuration space of closed strings. Okay. And these are well understood. There are long ago mass papers from which has given a presentation of these groups. Okay. and they are the kind of groups which come in quantum gravity. Okay. This is a more easy model of the kind of groups which come in quantum gravity and its configuration spaces. So, these are modeling this, the configuration space of loops like this in 3 dimensions is a skeletal model for the kind of things that happen in quantum gravity, and even this is not well understood at the level of quantum theory. Okay. It is not a question of quantizing the loops, okay. That is a string activity, that is not relevant, may be relevant, okay. But even just this topological aspect of the braiding, okay, but the fundamental group of these spaces, and how do you handle it, what are its representations, is not known, okay. It is not understood. So, today I will stop here, and next time, next Tuesday, I will try to move towards QCD and towards quantum gravity, okay. QCD theta angle and quantum gravity.